In January 2010, inside the Natanz uranium enrichment plant in central Iran, inspectors watched technicians remove broken centrifuges from the cascade halls. The machines are supposed to spin with extreme precision. Instead, more are failing. Nobody in the room seems to know why. 5 months later, a small antivirus company in Belarus receives a strange call. Computers in Iran are crashing and rebooting. The files they find will change what a computer virus can be. This is the story of Stuxnet. Natanz is not a normal factory. It is built around centrifuges, tall metal cylinders that spin uranium gas at extremely high speed. The machines separate isotopes inside uranium hexafluoride. One form can be used for nuclear fuel. If pushed far enough, it can also become part of a weapon. Iran has always said its nuclear program is peaceful. The United States, Israel, and several other governments have not believed that by the late 2000s. Natanz has become one of the most watched industrial sites on Earth. Satellite analysts study it, diplomats argue about it. Inspectors count machines, but what matters most is hidden inside the cascade halls. The Ur-1 centrifuge is a fragile machine. It spins so fast that tiny vibrations matter. A slight change in speed can create stress. A slightly wrong pressure can damage the process. A single failing centrifuge can contaminate the cascade around it, so the plant relies on control systems. Computers monitor valves, pressures, motor speeds, alarms, and safety states. Operators sit in front of screens and trust what they see. If something goes wrong, the system is supposed to tell them. Stuxnet was built to make that trust useless. It did not begin like a movie. There was no explosion, no blackout, no warning siren across the desert. It began as code moving through Windows computers, removable drives, shared folders, engineering stations. And industrial software. This is the strange part. Natanz was not supposed to be casually reachable from the internet. Facilities like this are separated. Engineers call it an air gap. The most sensitive machines are isolated from ordinary networks. But humans cross gaps. Contractors carry laptops. Technicians use USB drives. Project files move from one machine to another. Stuxnet used that. On July 15, 2010, security researchers started warning about a new Windows shortcut flaw. A USB stick did not even need to be opened in the normal way. Windows only had to display the shortcut icon. That was enough for the malware to run. For ordinary malware, this would already be serious. For Stuxnet, it was just one door. The worm carried multiple exploits. It used stolen digital certificates. It spread across local networks. It updated itself peer-to-peer. It looked like a general infection, but that was misleading. Most infected computers were just the road. The destination was Siemens Step 7. Step 7 is engineering software used to program programmable logic controllers. Or PLCs. A PLC is a small industrial computer. It does not write emails or browse websites. It opens valves, reads sensors, changes motor speeds, and keeps physical equipment inside limits. If a desktop computer is a clerk, a PLC is a hand on a machine. Stuxnet reached for that hand, inside the infected engineering station. Stuxnet replaced a Siemens software file with a malicious version. That let it sit between the engineer and the PLC. When code was written to the controller, Stuxnet could change it. When the engineer read code back, Stuxnet could hide the change. It was not just a Windows rootkit. It was a PLC rootkit. That was new. Most malware steals, some malware deletes. Stuxnet waited for a very specific industrial fingerprint. It checked for Siemens controllers. It checked the way frequency converter drives were arranged. It checked whether the motors were running in the range used by high-speed centrifuges, if the machine was not right. It mostly passed through. This is why it infected computers all over the world but attacked almost nothing. A normal virus is greedy. Stuxnet was picky. When it found the right system, it changed the physical process. One attack sequence manipulated the speed of centrifuges. The machines would run normally for long periods. Then, at carefully chosen intervals, Stuxnet would push them outside their normal behavior. Later, it would bring them back. The operators would look at their screens. The screens would lie. This was the most elegant part of the weapon. Stuxnet did not only change the machinery, it also replayed normal-looking data to the people watching it. If the centrifuges were being strained, the control room could still see a calm machine. If the motors were doing something dangerous, the screen could still show routine operation. The machine was screaming in a language the operator could no longer hear. At Natanz, the damage was strange. Centrifuges were failing, but not in a way that looked like a bomb. Parts broke, machines had to be removed, cascades had to be repaired. Iranian technicians replaced equipment without necessarily knowing that the cause was software. That is the design. Stuxnet did not need to destroy the entire plant in one day. It needed confusion. If a machine breaks because of sabotage, you search for an enemy. If a machine breaks because of engineering, you search your own work. You check bearings. You check valves, you check materials, you check operators, you blame maintenance for a while. The attacker gets something better than damage. They get doubt. Reports later suggested that in late 2009 or early 2010, around 1,001 centrifuges may have been destroyed at Natanz, out of roughly 9,000 deployed at the site. The number is debated because almost everything about Natanz sits inside secrecy, intelligence, and national pride. But the pattern was difficult to ignore. The worm had hit something real, then it escaped. That was the mistake. Or at least the thing that made the secret public. Stuxnet had been designed to move aggressively enough to reach a closed facility. But once it moved too far, it became visible to the outside world. It spread beyond the intended path. Security companies began collecting samples. Researchers started pulling it apart. At first, they did not know what they had. There were strange files, there were drivers, there were command servers, there were stolen certificates from real hardware companies. There were functions that seemed excessive for ordinary crime. No bank accounts, no ransomware note. No obvious theft. Then researchers found the PLC code. The story changed. Ralph Langner, Symantec researchers, Esset, Kaspersky, Microsoft, and others began mapping the weapon. They saw how much effort had gone into it. This was not a teenager with a laptop. This was not a criminal group trying to steal passwords. This was an operation with money. Industrial knowledge, testing infrastructure, and intelligence about a specific facility. Someone had to know the target hardware. Someone had to know the centrifuge process. Someone had to test the attack before releasing it. That is why Stuxnet is so important. It was not the first cyber attack. It was not the first piece of malware to hit industrial systems. But it was the first widely known malware that crossed the line so clearly. Code entered computers and physical machines broke. A worm had become a weapon. The suspected authors have never officially stood in front of cameras and signed their work. Many reports have pointed to a joint American and Israeli operation. The name Olympic Games is often connected to it. Former officials have spoken around it, journalists have reconstructed parts of it, but the public record still has gaps. That is also part of the weapon. Attribution is smoke. In conventional war, a missile leaves wreckage. It has serial numbers, flight paths, launch signatures, radar trails. In cyber operations, the evidence is different. Code can be copied, servers can be routed through other countries, language clues can be planted, time zones can mislead. Even when experts are confident, governments can deny everything. Stuxnet lived in that space. Iran did not respond by shutting down its nuclear program. Natanz recovered. New centrifuges were installed. The enrichment dispute continued, diplomacy continued, sanctions continued, sabotage continued in other forms. The attack may have delayed part of the program, but it did not end the story. Instead, it taught the world a lesson no one could unlearn. Industrial control systems were everywhere: power grids, water plants, oil pipelines, rail networks. Hospitals, factories, ships, airports. Most were designed for reliability first, security second. Many were built in a world where isolation was assumed. Then they were connected, patched, remotely maintained, and quietly made reachable through ordinary people doing ordinary work. A contractor plugs in a laptop. A technician opens a project file. A USB drive crosses a gate. That is enough after Stuxnet. Security researchers looked at industrial systems differently. Governments looked at cyber weapons differently. Militaries looked at keyboards differently. If code could spin centrifuges out of control in Iran, code could do something else somewhere else. It could open breakers, it could poison data, it could stop pumps. It could make operators trust a screen at the exact moment they should not. The most unsettling part is not that Stuxnet was sophisticated. It is that it was specific. It showed that digital weapons could be engineered like custom tools, not just malware for computers. Malware for a room, a process, a machine, a country's most sensitive project, and once a tool exists. Other people study it. Stuxnet was discovered. Its methods were documented. Its ideas became part of the public imagination. Researchers learned from it, defenders learned from it, attackers learned from it too. The code itself could be studied. But the larger idea was harder to contain. You do not need to copy Stuxnet to learn from Stuxnet. That is why the story does not end at Natanz. It starts there. The facility in the desert was repaired. The broken centrifuges were replaced. The worm was named, dissected, archived, and turned into conference slides. But the logic behind it remained loose in the world. Find the trusted system, make it lie. And let the machine destroy itself while the screen says everything is fine, somewhere right now. Another operator is watching another screen. It looks normal.